Hey Honors Physics, this is Mr. Hausman. Let's take a look at another angled projectile launch, and let's see if we can also notice some similarities between how we solved the previous one on the top of the page, number 12, and number 13. So let's talk about the scenario. We have a ball of some small size that is being thrown from the top of one building all the way up against the wall of a taller building that is 50 meters away. The ball was thrown at a velocity of v0 of 20 meters per second at a 40-degree angle. Now I know that's a v0, not a vx or vy, because an angle is provided. As soon as there's an angle provided, it's implied that it is neither x nor y, but really the combination of those, right? The actual launch velocity. I want to know if you can find how far above or below the original level where will the ball land. So I guess one possibility is that it curves very slowly down and hits some position lower down than it started. I guess it could land up here, curve and come down against the wall. It could coincidentally land at the same level. That would be a delta y of 0, but we don't know which one of these is true. And furthermore, we could even predict that what if it's still rising? What if it actually isn't falling down into the wall? What if it's still on its upward trajectory? Well, any of those could be true, and all we have to do is calculate the delta y, and that will tell us whether it is above, a positive value. If it's below, or if it's 0, then it's at the same starting height. So let's move ahead and see what we can do. Let's organize a data table. Now, you probably are pretty good at these. We've got horizontal or x and y data. And we know that the way from the previous video to find Vx, because it is adjacent, Vx is adjacent to the 20 meter per second throw. Here's my Vx, that I must be using cosine of a 40-degree angle times the initial v0, or 20 meters per second. My v initial y is opposite. That would be up here. V initial y, when the throw is 20, and the angle is 40 degrees. So that would be sine of 40 times 20 meters per second. We know the displacement horizontally is positive 50 meters. It moves 50 meters ahead before hitting the wall. And we do not know the time. Let's see if we're going to be able to use that like we often do. Vy final or V final y, we don't know that. That would be wherever it hits the wall, what is the vertical component? And that would actually tell us which way it's going, but it's not actually asked. So we'll just leave that there. We'll put it in our list. We'll actually make it a little bit neater. And then we'll leave it in our list. So there's several ways you can write it, but I'm going to do V final y. Now we know the A in the vertical direction is negative 9.8. We know the delta y. Well, we don't know it, but we want to know it. There's our unknown. And we know that there could be a time, and these two times are the same time. The time to move sideways for a projectile is the same as the time to drop or rise. So the times are the same. So I hope you're noticing that you have 2 out of 3 variables in the horizontal direction. So I'm going to use the constant velocity formula, but I'm going to rearrange it to solve for t. T is equal to delta x over vx. So I get 50 meters over cos 40 times 20 meters per second. 50 divided by cos 40, close parentheses, times 20. Let's try that again. I think I messed up. Cos 50 divided by parentheses cos 40 and times 20. What I did accidentally on my calculator screen, and I know you can't see this, is I forgot to put this in parentheses. Because if you do 50 divided by cos 40 times 20, it thinks the 20 is in the numerator, not in the denominator next to the cos 40. So by putting it in a parentheses on your calculator, and I'm closing my parentheses now, there we go. Now we get a time equal to 3.265 seconds. And you can carry more decimal points if you want, or you can just leave it on your calculator screen. And that's a stepping stone. But if you like, we can put that in 3.2635 seconds, 3.2635 seconds. And now we have 1, 2, 3 pieces. 3 out of 5 means we're good to go. We can start trying to find delta y. So from the constant acceleration side of our equation card, delta y equals VIT plus 1/2 AT squared. Delta y is what we do not know. Sine 40 degrees times 20.
The practice was moved from the softball field to the batter's box in Hudson.
Sorry about that. Didn't know that was coming. That's time multiplied by the time, 3.2635 seconds, plus negative 4.9 t squared. Oops, we know the time. I made a mistake. There we go. And that would be, of course, parentheses 3.2635 quantity squared. Now, that's just a lot of simplifying, but I think we can do that kind of all together. So we'll take the time. I'm actually going to simplify the right side of that first, the right term, 3.2635 quantity squared times negative 4.9, and you get negative, let's try that again, negative 52.1877. And that's meters. If you're wondering, these are seconds squared. This is meters per second squared. The seconds squareds cancel out. You're left with meters. And then let's simplify and do it again. Okay, there's my time multiplied by sine 40 times 20. And on this side, the first term, I get 41.95498, again carrying extra decimals so as not to worry about rounding error. Now let's take our answer and then subtract from it the 52.18777, 0085 if you want to carry more digits, and I get a delta y of negative 10.23 meters, which tells us that the accurate depiction was in fact a negative delta y, and it is currently hitting the wall 10.23 meters below its original starting height.